Now we come to chapter 4. In this chapter, we will study Fredholm integral equation of second kind with symmetric kernel. This chapter is divided into two modules. In first module of this chapter, we will study some properties of symmetric kernel. Now we come to Fredholm integral equation of second kind as given by equation 4.1. Here the kernel kxt is a symmetric kernel. Now equation 4.1 can be written in the operator form as I minus lambda capital K phi equal to f. Here I is the identity operator, capital K is linear integral operator given by equation 4.2. Now what is called a symmetric or Hermitian kernel? This we have discussed in previous modules. Now we give the proper definition. A complex valued kernel kxt where x and t lies in the closed interval ab is called a symmetric or Hermitian kernel of an integral equation if kxt is equal to k bar tx, where this bar denotes the complex conjugate. In this situation, the integral equation is also called a symmetric integral equation. Moreover, if kxt is a square integrable kernel where x and t both lies in the interval ab, then kxt is called the Hilbert-Smith kernel. Now we consider some examples of Hermitian or symmetric kernels. First example is given by kxt equal to x plus t. So naturally here k bar tx is equal to kxt. In the next example, kxt is equal to I into x minus t, where I is the imaginary unit, and here also we can verify that kxt is equal to k bar tx. Next example, kxt equal to e to the power x plus t. This is obvious, kxt equal to k bar tx. In fourth example, kxt is equal to t when t is less than x and x for x less than equal to t. Here also we can verify that kxt equal to k bar tx. Similarly, in the last example, kxt equal to x into 1 minus t for x less than t and t into 1 minus x for x greater than equal to t. Here also we can verify that kxt is equal to k bar xt. So we have learned what is called a symmetric or Hermitian kernel, and we have given some examples for symmetric kernel. Now we shall study some properties of symmetric kernel which will be given in form of 4 theorems. Now we come to theorem 4.1. It states that for all Hermitian or symmetric kernels kxt, the following property holds, that is, the inner product of capital K phi and psi is equal to inner product of phi and capital K psi, where capital K is an integral operator, and phi and psi denotes the inner product of two square integrable functions phi and psi. Now we prove this result. Let kxt be a symmetric kernel. That means kxt is equal to k bar tx. Now we observe that the inner product of capital K phi and psi is equal to integral from a to b capital K phi t into psi bar t dt, where bar denotes the complex conjugate. From equation 4.2, we have learned what is the capital K phi operator. That is, capital K phi is given by equation 4.2, that is, it is integral from a to b small kxt into phi t dt. So we use this operator to write the inner product of capital K phi and psi equal to double integral, where the outer integral is from a to b psi bar t dt, and the inner integral is from a to b k ts phi s ds. Now we interchange the order of integration so that the t integral will be the inner integral and s integral will be the outer integral, so that the inner product of capital K phi and psi, that will be equal to integral from a to b phi s ds, and the inner integral is from a to b k ts psi bar t dt. This can be written as integral from a to b phi s ds, and the inner integral we can write as integral from a to b k bar ts psi t dt whole bar. That means we take the complex conjugate of the whole of inner integral. Now since kst is the symmetric kernel, so in the inner integral, in place of k bar ts, we can write kst. So the inner product of capital K phi and psi is equal to integral phi s ds, and the inner integral is integral from a to b kst psi t dt, and bar is on the whole of inner integral, so that this can be written as from integral a to b phi s, and the inner integral now becomes k psi s bar ds, so that this is the inner product of phi and k psi. Thus we have proved that inner product of capital K phi and psi, this is equal to inner product of phi and capital K psi. Now we come to remark 1. In chapter 3 module 6 in theorem 3.4, we have already proved that the inner product of capital K phi and psi, this is equal to the inner product of phi and k star psi as given by equation 4.3. Here k star phi x is the adjoint operator corresponding to capital K, and this is given by k star phi x equal to integral from a to b k t x bar phi t dt. Now, if we compare the result of theorem 4.1, that is inner product of k phi and psi, this is equal to inner product of phi and k psi, with equation 4.3, then we can see that the integral operator k is equal to its adjoint operator capital K star. That means the operator involving Hermitian or symmetric kernel is a symmetric or self-adjoint operator, and hence every Fredholm integral equation of second kind also represents its adjoint equation. In view of this, we can say that Fredholm theory, which holds for continuous or square integrable kernel, is also valid for symmetric kernel. Next, we come to theorem 4.2. In theorem 4.2, we will show that all iterated kernels of a symmetric kernel are symmetric. Now, for proof, we suppose that the kernel kxt is a symmetric kernel. Hence, the first iterated kernel is denoted by k1xt, which is equal to kxt. And if it is symmetric, then we have the result that k1xt is equal to k1 tx bar. So, the first iterated kernel is a symmetric kernel. Next, we come to the second iterated kernel, k2xt. This is given by integral a to b k1xs into k1st ds. Now, since the first iterated kernel is symmetric, so we can write this integral as integral from a to b k1 bar sx into k1 bar ts ds, which can be written as integral from a to b k1 ts into k1 sx bar ds, which is equal to k2 tx bar. So, this shows that the second iterated kernel is also a symmetric kernel. This is based on the fact that the first iterated kernel, that is the original kernel, is symmetric. Next, we shall show that the third iterated kernel, that is k3xt, it is also symmetric. Now, k3xt is defined as integral from a to b k2 xu into k1 ut du. Now, we write the expression for k2 xu, so that k3xt becomes integral from a to b k1 ut du into the inner integral from a to b k1 xs into k1 su ds. So the inner integral we write in place of the second iterated kernel k2 xu. Now we interchange the order of integration. That means S integral becomes the outer integral and U integral becomes the inner integral, so that k3 xt is equal to integral from a to b k1 xs ds, and the inner integral is from a to b k1 su into k1 ut du. Now here you notice that the inner integral is k2 st, so that k3 xt becomes equal to integral from a to b k1 xs into k2 st du. Now we know that k1 xs is a symmetric kernel and also k2st is a symmetric kernel, so that we use this property to write k3xt equal to integral from a to b k1 sx bar into k2 ts bar ds, which can be rewritten as from integral from a to b k2 ts into k1 sx bar ds, which is equal to k3 tx bar. So we have shown that k3 xt is equal to k3 tx bar. That means the third iterated kernel is also a symmetric kernel. This is proved based on the fact that k1 xt is a symmetric kernel mainly, and also k2 xt is a symmetric kernel. So if we proceed in a similar manner, we can prove the theorem for all iterated kernels. Next we come to the third property, which is in form of theorem 4.3. This theorem states that every eigenvalue of a symmetric kernel is real. So for proof, let us assume that lambda naught is an eigenvalue of a symmetric operator capital K, and phi naught not equal to 0 is the corresponding eigenfunction. Then phi naught satisfies the homogeneous Fredholm integral equation of second kind given by phi naught x minus lambda naught capital K phi naught x equal to 0, x lying in the interval a to b as given in equation 4.4. Now we multiply both sides of equation 4.4 by phi naught bar and integrate with respect to x from a to b to obtain integral from a to b phi naught x into phi naught bar x dx, that is equal to lambda naught into integral from a to b k phi naught x into phi naught bar x dx. The left hand side is the norm of phi naught, square of the norm of phi naught, and right hand side is lambda naught into inner product of k phi naught and phi naught. So from this we can write the eigenvalue lambda naught equal to norm phi naught square divided by inner product of k phi naught and phi naught as given by equation 4.5. Again, from equation 4.4, if we take the complex conjugate, then it can be written in the form as given by equation 4.6. Now we multiply equation 4.6 by phi naught x in both sides and integrate with respect to x from a to b to obtain integral from a to b phi naught x into phi naught bar x, that is equal to lambda naught bar integral from a to b capital K phi naught x bar into phi naught x dx. The left hand side is the norm of phi naught square and right hand side is lambda naught bar into the inner product of phi naught and capital K phi naught. Now, if I use the result of theorem 4.1, then the inner product of phi naught and capital K phi naught, it can be written as inner product of K phi naught and phi naught, so that we get norm of phi naught square minus lambda naught bar into the inner product of K phi naught and phi naught equal to 0. From this we get lambda naught bar equal to norm of phi naught square divided by K phi naught, that is the inner product of K phi naught and phi naught as given by 4.7. Now, if I compare equation 4.7 with equation 4.5, we find that lambda is equal to lambda naught bar as given by 4.8, that is lambda naught bar equal to lambda naught, and this shows that lambda naught is a real quantity, and if lambda naught and phi naught exist, that means the eigenvalue lambda naught is a real quantity for phi naught not equal to 0. So, we have proved that eigenvalue is real. Next we come to the fourth property, that is theorem 4.4, which states that the eigenfunctions of a symmetric kernel corresponding to different eigenvalues are orthogonal. For proof, we assume that lambda 1 and lambda 2 are two different eigenvalues and phi 1 and phi 2 are their corresponding eigenfunctions respectively associated with the symmetric kernel kxt. Then phi 1 and phi 2 will satisfy the homogeneous Fredholm integral equation of second kind, so that we get phi 1 equal to lambda 1 capital K phi 1, where x lies in the interval a to b as given by equation 4.9, and phi 2 is equal to lambda 2 into capital K phi 2, x lies in the interval a to b as given by equation 4.10. Now, we multiply both sides of equation 4.9 by lambda 2 bar into phi 2 bar x and integrate with respect to x from a to b, we obtain on the left hand side that lambda 2 into inner product of phi 1 and phi 2. Here we note that the eigenvalues are real. So the left hand side of equation 4.11 is lambda 2 into inner product of phi 1 and phi 2, and that is equal to lambda 1 into lambda 2 into inner product of capital K phi 1 and phi 2, which is given by equation 4.11. Next, we multiply both sides of equation 4.10 by lambda 1 bar into phi 1 x bar and integrate with respect to x from a to b, and we note that the eigenvalues are real, so that we get lambda 1 into inner product of phi 2 and phi 1, which is equal to lambda 1 into lambda 2 into the inner product of k phi 2 and phi 1. Now we use the theorem 4.1 so that we can write the inner product of k phi 2 and phi 1 is equal to inner product of phi 2 and k phi 1. So we obtain equation 4.12, which is given by lambda 1 into inner product of phi 2 phi 1 is equal to lambda 1 into lambda 2 into inner product of phi 2 and k phi 1. Now if we take the x conjugate on both sides of equation 4.12, we will find that lambda 1 into inner product of phi 1 and phi 2, that is equal to lambda 1 into lambda 2 into inner product of k phi 1 phi 2 as given by equation 4.13. Now we take the difference of equation 4.11 and 4.13. 4.13 is here and 4.11 is here, so that we get lambda 1 minus lambda 2 into inner product of phi 1 and phi 2 is equal to 0, which is given by equation 4.14. Now we have assumed that lambda 1 is not equal to lambda 2, so we get the inner product of phi 1 and phi 2 equal to 0. This shows that if the eigenvalues are not equal, then the corresponding eigenfunctions are orthogonal. Hence, the theorem is proved. So we conclude this module, and in this module we have learned what is called a symmetric kernel along with some examples. Also, we have learned some properties of symmetric kernel in this module.